Hi, welcome back to my channel, and in today's video I'm going to show you how to find the exact value of the series of -1 to the n times 6n all over 4 to the n, obviously where the series goes from 1 to infinity. Now I'm going to assume that you can already confirm that this series converges. If not, then of course finding the sum is pointless. If you're not sure, go ahead and give that a try first. In order to do this, we're going to follow a 6-step process as identified here, where first we're going to list out the terms, then we're going to reorganize the terms into groups, hopefully be able to find patterns of those groupings, and then try to change those patterns into a new rewrite of the series, simplify the series down to use our identities that I used in the previous video that I established in the previous video, and then actually evaluate. So first, let's list our terms. And that's easy enough. We're just going to plug 1 in, then plug 2 in, then plug 3 in, and so forth, creating this list. And you'll notice I'm not going to evaluate each of those computations because it tends to be easier, at least in my opinion, to rewrite them when you can see all the terms listed out like this. It's much easier to find patterns, in other words. And so one thing you may notice is that every other term is negative, and another term is positive, which means I can probably break these into two groups, a negative group and a positive group. And in doing so, I may be able to find patterns that could represent each group independently of each other. And of course, we can do this kind of reorganization because we know it's convergent, which is why it's very important that you can establish early on that the series does converge. If it doesn't converge, then reorganizing it can actually compute with some really bizarre values. So let's try to identify what patterns we notice. And we notice on the negative side, I always have that -1 times 6 in the numerator, meaning I always have a -6. And then I also have that scalar value of 1357, which means that's always an odd number starting at 1. And the denominator is similar in that the exponent is 1357. So the denominator can be characterized as having a 4 with an odd power, obviously starting at 1. Now let's see if we can kind of break down how the positive side is working. And on the positive side, you might notice that there's always a 1 times 6 in the numerator. And then we go 2, 4, 6, 8, 10, and so forth. So the scalar value starts at 2 and is all the even numbers. Denominator, in a very similar sense, is 4 to those even values starting at 2. So now that we've found the patterns of each group, let's see if we can do a rewrite of each group as their own independent series. So in the first one, we know we have -6 in the numerator every time. And then I need to write some representation of that odd number starting at 1 and the denominator with the odd number starting at 1. For the positive side, we always have a 6 in the numerator, and then we have a numerator scalar starting at 2. So 2 times something, then 4, then 6, and so forth. And the denominator would be 4 to some kind of power in the same format. Putting it all together, we see we can create these two series. So notice I have the -6, and then 2n minus 1 represents the odd values. And so 4 to 2n minus 1 will give me the odd powers for the 4. In the bottom case here, I have the 6 always, and then 2n for the even numbers, and 4 to the 2n for the even powers of the 4. So therefore, this original series can be broken down into these simpler series. And you'll see why they're simpler in a little bit. I know it's a lot of numbers going on, but it actually does make life a lot easier. So now that we rewrote them into series that are much more familiar to us, much more like the ones in the previous video, we can now go about attacking these and eventually finding an evaluation for them. So let's simplify it. First thing I'm going to do is multiply through by those 6's. Give me the series of -12n plus 6 over 4 to the 2n minus 1 as my first series, and then 12n over 4 to the 2n as my second series. And much like before, I want both of these series to have the same kind of denominator. It helps a lot when you try to combine series if the denominators are the same. So I need to get rid of this -1 here. And like we established, when it's a -1, that means it's 4 to the -1 power in the denominator, which actually means it translates to being a coefficient of 4. And so I can just pull out a 4. Okay. Now what I want to do is break apart that 12n, that -12n plus 6, into 2 separate series. So that way I have 3 series that are very familiar in form to how we've been solving these in the previous video. And of course, that's easy enough. I can simply split them apart to 2 separate series, not forgetting to bring that 4 as a distributing factor to both of these. So now my first series expression is for the summation of -12n over 4 to the power of 2n times 4, and the summation of 6 over 4 to the power of 2n times 4. And then we still have that 12n over 4 to the 2n as a summation too. Okay, so now we're slowly getting these things to be very similar, so we can try to combine things that we can. And one thing you may notice is that first and last one are very similar. In fact, if I can just get this negative pulled out, I'll have 12n over 4 to the 2n on both the first and third expression. So let's do that. And now that they're both the same exact kind of series, I can combine them into a single series. Breaking this down to very simple, 4 times the summation of 6 over 4 to the 2n minus 3 times the summation of 12n over 4 to the 2n. Now to have it in the final form I'm referencing, I'm going to simply distribute the 4 and 3 back in, giving me 24 over 4 to the 2n as a series and 36n over 4 to the 2n. And now we're at the very final stage to get it in the exact form I'm referencing. And for those who are not exactly sure what I meant by the one I'm referencing from the identities, you can check out my video here, and you can see how I established those identities I'm about to show you. But since it's 24 over 4 to the 2n, 4 to the 2n can be rewritten as 16 to the n, because you can just distribute this 4 squared and 4 squared, giving me two very simple series of 24 over 16 to the n and 36n over 16 to the n. Now, these are in the form that we actually need to solve the question. So this original series can be rewritten as the summation of 24 over 16 to the n minus the summation of 36n over 16 to the n. And as I established, and I keep referring to my previous video, we established these 3 facts that we can simply pull together and get our solution. So in the first case, 24 over 16 to the n is obviously this original geometric identity, where the constant times 1 over 1 minus the denominator, or denominator minus 1, I should say. So it would be 24 times 1 over 16 minus 1. And in the second case, we have a coefficient of 36, and so it'll be 36 times 1 over 15 plus 1 over 15 squared. Or in other words, this. And with some careful evaluation, we see it comes out to -24 over 25. And just for fun, we can verify Wolfram Alpha and find out that we are in fact correct. All right, this is a much shorter video, everybody, so I hope you enjoyed it. Thank you for watching and have a great day.